Hello everyone and welcome back to Math Made Easy. In our previous lectures, we studied numerical differentiation using the forward difference and central difference formulas. Today we are going to complete the first derivative formulas by studying the backward difference formula. We will first understand when to use it, derive the formula using the Taylor series, and discuss its order of accuracy and solve the numerical example stepwise. So suppose we have equally spaced values of x as is x0, x1 and up to xn with the constant spacing as h, which is equals to xi minus x of I minus 1. And suppose we want to calculate the derivative at some point xi. So for the forward difference, we use the points ahead of xi. And for the central difference, we use points on the both side of xi. But for the backward difference, we use the values behind the point. So the important points becomes this xi minus h, and xi minus twice of h. And this is particularly useful when the required point is near the end of the table. So before deriving the formula, let's just introduce the backward difference operator. So the backward difference of fi will be defined as this nabla fi equals to fi minus 1. Then the second backward difference is defined as this nabla square fi equals to nabla fi minus nabla fi minus 1, which gives this as fi minus twice of fi minus 1 plus fi minus 2. And similarly, we got this nabla cube fi equals to fi minus thrice of fi minus 1 plus thrice of fi minus 2 minus f of I minus 3. And these backward differences will help us understand the derivative formula. Now let's just derive the backward difference formula. So we just started with a Taylor expansion of f of xi minus h about xi. So we get this f of xi minus h equals to fxi minus h times f dash xi plus h square by 2 factorial f double dash xi minus h cube by 3 factorial f triple dash xi and up to so on. And after rearranging, we got this h times f dash xi as this f of xi minus h plus h square by 2 factorial f double dash xi minus h cube by 3 factorial f triple dash xi and up to so on. Now just dividing by h, we got this f dash xi as fxi minus h divided by h plus h by 2 f double dash xi minus h square by 6 f triple dash xi and up to so on. Now just ignore the higher order terms. So we obtain this f dash xi as approximately equals to fxi minus h divided by h. And this is the first order backward difference formula. So we can also write the formula using the backward difference operator. And since this nabla fi is fi minus 1, so we have this f dash xi approximately equals to nabla fi divided by h. And this is one of the most important formulas in numerical differentiation. Now let's just identify the truncation error. From our derivations, the first neglected term is as this h by 2f double dash xi. Therefore, the truncation error becomes this order of h. So the backward difference formula is the first order accurate. Now let's just compare the three first derivative formulas as is forward difference as f dash xi approximately equals to fi plus 1 minus fi divided by h, and hence this error becomes order of h. And then comes the backward difference where this f dash xi is approximately equals to fi minus 1 divided by h, and hence the truncation error becomes this order of h. And now comes the central difference where this f dash xi is approximately equals to fi plus 1 minus fi minus 1 divided by twice of h, and hence this error becomes order of h square. So the central difference has a higher order of accuracy than the basic forward and backward formulas. Now comes the very important practical question: when should we use this backward difference formula? So suppose our table look like this: x0, x1, x2 and x3, x4. And if we want to find the derivative near the last point, say x4, so we have plenty of data behind it. That says x2, x3 and x4. So the backward formula is convenient. Now we have a question here where we have given this tabulated data as this x values as 1, 1.1, 1.2 and 1.3. Then comes this fx values as 2.7183, 3.0042, 3.3201 and 3.6693. And you need to determine the value of f dash 1.3 using backward difference formula. So since we need this f dash 1.3 and this 1.3 is actually the last point in the table, so the backward difference is appropriate. So first calculating this h value, which is this 1.3 minus 1.2 as 0.1, and now we can use this f dash xi as approximately fi minus 1 divided by h, and therefore we get this f dash 1.3 is approximately equals to f of 1.3 minus f of 1.2 divided by 0.1. Now just substituting, so we get this 3.6693 minus 3.3201 divided by 0.1 as 0.3492 divided by 0.1, and hence we got this f dash 1.3 as 3.492 approximately, and that's our backward difference approximation. Now before move on to the next section, let's just briefly see what something important. So the basic backward difference formula is basically this f dash xi, but we can obtain a more accurate information approximation by including the higher order backward differences, and the higher order backward formula for the first derivative will be like this f dash xi is approximately equals to 1 by h times nabla fi plus 1 by 2 times nabla square fi plus 1 by 3 times nabla cube fi plus 1 by 4 times nabla 4 fi to so on. And this comes from differentiating the Newton backward interpolation formula. We will study these higher order derivative formulas separately in the next section, so don't worry if this looks unfamiliar right now. So, and with that, we have completed the first derivative finite difference formulas, these backward, forward, central differences. And next lecture, we will move forward to the higher order derivatives, beginning with the second derivatives and deriving its forward, backward, and central difference formulas. So, if you found this lecture helpful, don't forget to like, subscribe to Math Made Easy, and keep practicing, and I'll see you in the next lecture.